Yeah, I'm Connor Fredrick, postdoc with Scott Diddams at NIST and CU Boulder. And also for this project, we are collaborating with the groups of Ryan and Suvrith at Carleton College in Penn State. And this talk is going to be about our work on frequency comb calibrated laser heterodyne radiometry, which we are pursuing for precision spectroscopy and radial velocity measurements of the sun. The search for exoplanets is driven by questions that have a profound impact on humanity's place in the universe. And by studying other stars and exoplanets, we hope to gain a better perspective of our own solar system and ultimately come to an understanding of the origin and prevalence of life. In awarding half of 2019's prize to Mayor and Coelho, the Nobel Committee recognized the importance of those questions and honored an achievement that helped set in motion a series of exciting discoveries that continue to this day. Shown on the right is the data from their 1995 paper, in which they used precision spectroscopy to detect the first exoplanet around a sun-like star using the radial velocity method. And there are two primary methods used for the detection of exoplanets. Both methods monitor complementary aspects of the light from the host star, either the amount or the frequency. The transit photometry method detects dips in a star's brightness as a planet moves in front of its star. And the radial velocity method detects the Doppler shifts in a star's spectrum as it's pulled around by its companion planets. The transit method is responsible for the dramatic increase in the number of confirmed exoplanets in recent years due to big name space-based observatories such as Kepler and TESS. The radial velocity measurements, on the other hand, are restricted to ground-based telescopes. This technique has experienced a slow but steady rate of detections as the precision of their spectrographs has increased. The information provided is complementary as well, and is such that the transits give a measure of a planet's radius, and radial velocity gives a measure of a planet's mass. Combining those two measurements is an important goal of the community in the push to identify nearby exoplanets for follow-up studies of their atmospheres. Such studies are one of the main science objectives for the James Webb Space Telescope and represents an opportunity where we can truly start looking for the signatures of life. This explosion of transit detections in the last decade means that radial velocity needs to catch up. Some of that will just take more spectrographs, more time on telescopes, as these instruments can only observe one star at a time. But some of that will also take higher precisions. However, achieving high radial velocity precision is a complex problem. We wouldn't be here today if it wasn't. All of these things, everything has to be right. And while in the past, community has turned to the calibrators, frequency combs, and other precision calibration sources, as more of those come online, the EPRV community is quickly turning to the next set of problems, noise due to the stars themselves. For precision spectroscopy in the lab, we usually only care about a couple line shapes. Doesn't matter how you put them together, you always get some nice symmetric profiles. This is not the case on the sun and other stars. The surface of the sun is a complex and dynamic region, as seen in this video from DKIST, which has a cadence of about 1 minute per second. And also for scale, there's the continental US on the left. Surface granulation produces both regions of bright uplift with a positive Doppler shift and cooler regions of downflow with a negative Doppler shift. Adding these together gives the observed lines a shifting asymmetry, which is typically measured with a bisector. And fluctuations or perturbations of this process change the apparent Doppler shift of the line. They're just one aspect of stellar activity. Large-scale activity has important effects as well. Seen as these simulations show potential effects of sunspots, different regions of chemical abundances, and different types of pulsations or vibrations of the stellar surfaces, and those effects that they can have on the absorption lines. And more insidiously, these can be quasi-periodic with the rotation of the star. And there's been more than one candidate exoplanet that's turned out to be just this type of signal. Another example is magnetic activity, which has recently been identified as having strong correlations with measured radial velocities on the sun. Crucially, all of these different sources of activity have some kind of impact on the line shapes themselves. So can the information contained within individual line shapes be used to correct for that activity? And what does it take to measure those signatures? What spectral resolution, what cadence, what signal to noise ratio? This is where the Heterodyne radiometer comes in, which allows us to explore this problem with a high resolution instrument that isn't limited by the same systematic issues or constraints as traditional spectrographs. Being one of the closest stars to Earth, the Sun presents unique opportunities for testing techniques for disentangling activity signals from spectral measurements, as high resolution imaging allows for independent identification and characterization of the sources of activity on the solar surface. While we haven't actually tried to back out this information yet, the rest of this talk will be about the instrument we're using to try to get there. Laser heterodyne radiometry achieves high-resolution spectroscopy by mixing or heterodyning thermal light with a laser. Light from the sun is first coupled into a single-mode fiber and is combined with the laser on a balanced photodetector. Through the heterodyne process, the local oscillator laser converts spectral information from a small region around its frequency to the RF baseband. Processing the result with a few simple radio frequency components, a low-pass filter, square law power detector, and integrator provides a signal proportional to the power within the optical bandwidth 2B, about the laser frequency. The full spectral profile can then be reconstructed by scanning this laser frequency. For our system, we use a 100 megahertz low-pass filter, and along with the response of the photodetector, this sets a point spread function shown here, which has a double-sided optical bandwidth of 200 megahertz, or a resolving power of about 1 million in the 1.5 micron region. And that's pretty good for a spectrometer that takes up less than a square foot. Can easily be less if the electronic components were all integrated together. This heterodyne resolution comes with a trade-off. We are limited to the information contained within a single spatial mode of the thermal source. This single mode limit is only reached when the receiver is spatially mode matched to the thermal source, something that is much easier to do on the sun than on other stars, given the constraints of the antenna theorem. The antenna theorem states that the product of the effective aperture or cross-section of the receiver and the effective acceptance angles or field of view is equal to the square of the wavelength. The thermal mode is maximally coupled when the thermal source completely fills this field of view. The single spatial mode of the fiber then contains one thermal mode's worth of photons given by the Bose-Einstein distribution. That means we're limited to the power of a single thermal mode, which for the sun is only a few nanowatts per nanometer. The signal to noise ratio is given by a simple equation. And in comparison to traditional spectrographs, which I've put up above, the important difference is that the SNR scales linearly with the number of photons instead of with the square root. That linear scaling is nice when you're heterodyning with another laser with lots of photons, but the thermal mode from the sun at 1.5 microns only has a photon density of less than 1 per second per hertz. So this bandwidth and averaging time do most of the heavy lifting. Both of these parameters can be set electronically. In general, heterodyne radiometry is more favorable at longer wavelengths, where the lower energy per photon leads to a greater number of photons and a lower sensitivity to loss due to a saturation of the signal-noise ratio from photon bunching. And historically, most heterodyne radiometry has been done in the radio or millimeter band. At 1.5 microns, the average number density from the sun is only 0.2. And we find ourselves just on the edge of the SNR roll-off at shorter wavelengths. With the basics of LHR out of the way, I'll talk about how we bring frequency combs into this. Frequency combs get their name by the distribution of their spectrum in the frequency domain. Along with an integer comb line number, the position of all comb teeth are described by 2 degrees of freedom, given by the stability of or timing of the pulse envelope and of the phase. This is the repetition rate frequency and the offset frequency. Since the repetition rate and the offset frequency typically lie in the radio frequency band, they can be measured and controlled electronically. This means that the same applies to all optical comb teeth as well. And given a suitable radio frequency reference, traceable to the SI second, such as an atomic clock or GPS, the stability of the SI second can be linked to all optical comb teeth, providing unparalleled long-term calibration accuracy. With a frequency comb, it becomes nearly trivial to measure the absolute optical frequency of another laser. We do this by measuring the difference frequency between a laser and one of the comb lines. Through the comb equation, this transforms the measurement of optical frequency into one of radio frequency, which is as simple as electronically counting the number of cycles or the phase within a set time interval. These kind of measurements revolutionized precision spectroscopy and led to the 2005 Nobel Prize awarded to Ted Hansch from Max Planck Institute and John Hall from here in Boulder. Since then, the study of laser frequency combs has branched out to more than just optical frequency measurements. This is a figure from a review article that came out around the 20th anniversary of the frequency combs invention and shows many different areas of spectroscopy where combs have now become indispensable. Well, this talk is going to focus on just this central branch. Astronomical spectrograph calibration and the search for exoplanets is just one of many intertwined applications and technologies enabled by frequency combs. Our group's primary expertise is in these combs. You've no doubt heard about these devices for spectrograph calibration. In particular, we are responsible for the comb system on the HPF spectrograph, which is now over 5 years running. However, these kind of combs are unique devices with mode spacings designed to be resolved by the spectrographs. As seen on the following slides, the frequency comb used for the Heterodyne project has a repetition rate 100 times smaller, which makes it much easier to use as a general purpose lab tool. We integrate the frequency comb into our system as a second LHR channel. And using the same local oscillator laser, we map out the solar spectrum and the spectrum of the frequency comb. The time domain data is recorded simultaneously on an oscilloscope and looks like the plot in the upper right. The calibration procedure involves fitting a Gaussian profile to each line to find its center and then interpolating a frequency solution between each comb tick. If we send the comb light into both of these channels, we can probe the calibration precision, providing an upper bound at the centimeter per second level for single scans, which averages down over time. Since we're in a sweeping configuration, only one point of the spectrum is being measured at any one time. We must be careful about slow amplitude fluctuations that could manifest as apparent frequency shifts. To mitigate this, we servo the power of the LO laser to the DC output of the photodetectors, controlling both the background level and the effective heterodyne gain. Additionally, we have placed the sensitive radiometric components, anything part of the conversion of optical power to voltage, in a thermally insulated box. This includes the photodiodes, RF amplifiers, frequency mixers. We still have a small bit of coupling to the ambient temperature, but on a scan-to-scan basis, the amplitude fluctuations are at the part per 10,000 level, relative to the amplitude of a solar signal. This gives us an equivalent noise floor of about 10 centimeters per second per scan. The coupling optics are housed on an autonomous solar tracker, seen in the photo at the bottom, which uses a quadrature sensor for active tracking from sunrise to sunset. As part of a two-stage solar tracking setup, we have an additional piezo-driven mirror for real-time optimization of the coupling into a single node fiber. That's located in this box on the right side. This piezo mirror dithers in a circular motion and uses lock-in detection to find the peak coupling. We want full disk integration for sun as a star measurements. For this, we use a flat top beam shaper. This is a refractive device that coherently transforms the Gaussian mode of the fiber into a more uniformly distributed pattern in the far field. This also has the benefit of making us much less sensitive to pointing errors as compared to the Gaussian mode, about 100 times less. Although I can't quite say that we're at this level at the moment, as we still have some mismatch between the expected and actual profiles that we're getting from the shaper. The observed profile has some prominent wings, which indicates that there's a slight mismatch between the actual and expected input beam sizes. So we still need to take a critical look or measure the actual sensitivity to this tracking precision, but we are still much better than the original Gaussian beam. As a test of the absolute frequency accuracy of our system, we utilized a laboratory reference cell, which is part of the standard reference material series from NIST, and it has a specified set of known lines. Instead of sunlight, we use an amplified spontaneous emission source, or ASE source, that consists of an unseated optical amplifier to give us incoherent light. Looking at the LHR measurements, this plot here represents the sum data of over 22,000 traces taken over a 36-hour period. The color here has been scaled to the density of points. You can see here that the residuals from the average follow a Gaussian distribution. Taking the cross correlation of the average spectrum with the individual traces, we can calculate the frequency instability. Plotting this as an Allen deviation, we see that this averages down to an uncertainty of 200 kilohertz. If we take the Coulomb equation, we can fit the center of this line, and we find that we have an absolute error of less than 2 megahertz from the published value for this reference cell, which is well within the plus minus 10 megahertz reported uncertainty. This system was used to observe a neutral iron line in the solar spectrum with a vacuum wavelength near 1565.28 nanometers. And we chose this line specifically for its very high magnetic sensitivity. The figure on the left represents the spectral profile and amplitude noise from an observing run that extended 20 minutes. This amplitude has been normalized to the background continuum level of 1, and the color has been scaled to density of points. The residuals with respect to the spectral template are plotted on the bottom, and the inset on the right again shows a Gaussian distribution. It's interesting to examine the solar data's signal-to-noise ratio as compared to the theoretical values for the thermal source. We find that plugging in the measured values for what the optical bandwidth was for this measurement, the averaging time per point, and the measured loss through the system, we find that our signal-to-noise ratio nearly exactly matches what is given by the quantum theory, and that this continues to average up over the entire observation window. If we look at the frequency oscillations of this data, we can see that we do also have the characteristic 5-minute period due to the solar P-mode oscillations. The single measurement traces give us a frequency uncertainty of about 7 megahertz in 10 seconds, just close to 10 meters per second RV instability. By averaging this over the 20 minutes, we do approach single meter per second level. But extending this to a longer time period is more interesting. With this, we used our improved solar tracker plus the beam shaper, and we're able to get data from sunrise to sunset, or at least until the sun goes behind the mountains behind Boulder. This data set also spans a larger spectral region. I'll get to that in the next slide, but this plot here shows 8 hours of data, and we've also changed the original low pass or averaging filter, which gives us a reduced single point SNR, but also gives us an effective, we effectively have 10,000 independently, statistically independent noise sources here. If we average that up over time, we also see that that has no problems. But if we look at the frequency shifts, we find that we have to calibrate or correct for this telluric contamination. And while the 1.5 micron region is considered an atmospheric window, it is hard to truly get away from water, especially at the high air mass. We fit this telluric spectrum to a few layer Hytran-based model that allows us to control and fit the temperature, pressure, and the water mixing ratios. We currently only fit once per day using these high air mass values. And we also mask out the solar line so as not to perturb that in the fits. If we add random changes to these values, we estimate that the residual telluric contamination then contributes a drift of only 3 centimeters per second over a 3-hour window. So looking at the corrected data, without the corrections, we run into a noise floor at about 1,000 seconds. But with these corrections, we were able to extend that averaging time to 3,000 seconds, almost an hour. We're still working to figure out what this limit is. But as seen in the following slides, it is not due to our instrument itself. And the way we know this is because we've also been concurrently looking at some atmospheric CO2 traces. And the line that's right around 1572 is one that's commonly used for remote sensing. Looking at the LHR trace of this, it is almost completely saturated where we're looking at it. But if we look at the time series of these traces, we actually see a roughly 2 megahertz per hour spectral shift throughout the day. What we found was that this is actually due to wind-induced Doppler shifts. And there have been some earlier papers or proposals that you could measure these sorts of things with LHR. Taking meteorological data from the European Center for Medium Range Weather Forecast Reanalysis, which gives us a 3-dimensional vertically resolved wind fields and temperature profiles. We can simulate what the line of sight wind speed is for our LHR measurements. And you can see here that for the upper atmosphere, we go from a positive wind speed to a negative wind speed as the LHR pointing angle shifts from east to west. We simulate the CO2 transitions and apply these Doppler shifts. We get a model that nearly lines up perfectly with our measured shifts. Subtracting that out and taking the Allen deviation of the residuals, see that we almost average down to 10 centimeters per second in about 2 hours. So the takeaway from that is that we are not limited by necessarily instrumentation or systematics, but by signal noise ratio and perhaps stellar activity or solar activity. Since the signal noise ratio is so important, it's good to ask whether we're actually doing this the best or most optimal way. And to really maximize the SNR, the best you can do is sit and average at a single point with a fixed bandwidth. That maximizes the averaging time for your particular region you're looking at. However, there's a problem with RVs is you have to consider that you need a change in slope to be able to differentiate or discriminate between two different locations. In general, there's a trade-off between bandwidth, resolution, and experimental complexity for different ways of getting these different, extending to different spectral bins. This first one here requires a large amount of digitization, can really only be applied over narrow spectral ranges because of that. But the final SNR you get would be something proportional to this single point SNR. With what we do with the scanning laser, we're dividing our averaging time over effectively a number of spectral bins. So that moderates the SNR, but does allow us to get a decent spectral range. It also means that there is very low digitization rates and data analysis. A third option would be to use 2 different combs, and I won't go into the details of this measurement, but basically because there's a different frequency spacing between each pair of comb lines, you can get what the spectrum is at these points. This allows you to do very wide spectral bandwidths for only moderate digitization rates. Going further, we could split these individual spectral regions and potentially use a frequency comb as the local oscillator instead of a second CW laser, where each comb tooth is split off into a separate channel. And one of these 3 methods is then used to subdivide that further. So I guess besides the sun, why would you want to do all this extra added complexity? One thing that it might enable is letting you extend this measurement technique to a handful of other stars. So the antenna theorem makes it difficult to do this, as when the source is unresolved, the SNR is going to decrease as basically the square of the ratio of the angular diameters. For instance, when we're doing the sun, it's actually kind of hard not to resolve it completely, as you only need less than a millimeter aperture to do so. But that millimeter can quickly become tens of meters for even the largest and the closest stars. So if you were on a moderate telescope, only a few meters, maybe in diameter, could you make up this factor of 10 by doing 100 different spectral channels? That'd be the open question there. Besides just spectroscopy, one niche area this could fit into is with phased array imaging. Just like the Event Horizon telescope that used millimeter waves and very long baselines, you could potentially do this in the mid-infrared or the near-infrared as well. And with baselines that would be too experimentally complex or expensive to do with directly combining the inputs of the two telescopes together. But if we go back to this scanning mode, the way that we're doing it right now, what can we do to make that the best that can possibly be? And one way is to just focus our averaging time on just the spectral regions with the greatest information content. And that's where the slope of the lines are the strongest. Because this doesn't give us enough bandwidth to measure the telluric lines, this particular test was limited to the just a couple hours around noon, where the air mass is minimized. And what we get by looking at the frequency shifts is that by starting with the better, more optimal averaging time, we get a better about 50% improvement, going from 15 meters per second to 10 meters per second in a 5-second trace. And we get to the 1 meter per second level in a shorter time period. If we further restrict this time series to a region that happens to have a flatter trend line, we see that the Allen deviation and the SNR supports a radial velocity precision down at 60 centimeters per second. If we were to push that further, what would be the result of narrowing down to only 2 points? The radial velocity information is maximized at the 2 steepest points of the line. And using some sensitivity arguments about SNR and that slope, we can optimize this SNR by increasing the optical bandwidth to just about that of the line width, or the full width half max. Running calculations using the line shapes for this transition, I estimate that the signal to noise ratio of this sort of measurement could ultimately support a 1 meter per second precision in only 10 seconds and a 10 centimeter per second in only 1,000 seconds of averaging. And that's just on the single line. And while this completely discards the line shape information, I think it's still an interesting limit nonetheless. An easy way to implement this in practice is to use what's called a dither lock. And this is similar to how spectroscopy is performed on atomic clocks, which involves dithering a laser and taking the difference between the amplitude on either side of a line. The differential amplitude is used to servo and lock the laser to the center of the line, with the laser frequency then directly counted and tracked against a frequency comb. Why this error signal shows up can be seen by taking a Taylor series expansion where we're centered at some point and we're modulating sinusoidally with some amplitude. The first term in this series is proportional to the derivative of the line shape multiplied by this modulation. If we take this signal, multiply it again by that modulation signal, this then collapses down to something that's proportional just to the derivative. And you can see this if we step through a few points here. So for below the resonance, if we modulate the X positive, we'll see that the signal that we get out goes negative. And this is a signal that is out of phase with the dither. So if we multiply this trace with this trace, we'll get something that is negative, which averages to something that looks like something on the left side of this plot. On resonance, the signal modulation ends up being twice the frequency of the modulation. And since sine of omega t is orthogonal to the sine at 2 times that frequency, this ends up averaging to 0, and we get the center of the error signal. Likewise, above the resonance, the modulation and the measured signal are both in phase, and the result is something that's positive. I've tested this with going back to this HCN reference cell. And in this case, I've modulated the laser frequency at a rate of 2 kilohertz, going 1 gigahertz peak to peak sweep amplitude. The optical bandwidth is roughly 500 megahertz, which is roughly that of the full width max of the line. And we count the frequency of the probe laser directly against the frequency comb. If we compare this with the results that were shown many slides ago, we show that this was a gives us roughly a 10x improvement in the uncertainty for the same averaging time, or equivalently a 100x less averaging time for the same uncertainty. We still run into roughly the same sort of noise floor. And in this case, that's most likely due to the ASC illuminator, which has a bandwidth that's roughly 100 nanometers, but has some large curvature to it. So with lab temperature changes, the central frequency of that slightly changes and ultimately changes the slope across the background. So that had kind of walked away from what we were originally going to do, or what we originally intended, which was these high resolutions of the line shape. With the dither lock, we don't have any of that information anymore. So at the same time, this dither lock, I think that the faster averaging of it will be very useful for testing systematics, as it would be difficult to diagnose and test for these things because at the levels we're at currently, it takes days of data to tell if we've made any improvement to the system or not. So I think ultimately, a combination of the scanned LHR, perhaps on one channel, and the dither lock on the same line, will give us a more ideal representation of what we can do. So in conclusion, I hope you got a better understanding or idea of what the LHR system can be and its capabilities. We are certainly excited to see how far we can push below 1 meter per second. For the near future, we already have the components in place to observe 2 lines in parallel. Intention there was to look at a high and low magnetic sensitivity line. And we are also working to streamline our data collection and processing so we can have a more regular cadence and start stringing days together, getting contemporaneous data with the other EPRV spectrographs. I think there are still paths towards the higher precision, particularly the configuration of the flat top beam shaper is somewhat preliminary, and it could be one of the issues we're dealing with at the long averaging times. There's in a single mode fiber, there's actually two modes. Right now, we're only looking at one of them, so we could increase our signal to noise by looking at both of those. And it's also, we could take more advantage of the targeted and narrow scans, particularly of the dither lock mechanism. And finally, I guess there's other directions that we could take this instrumentation. Instead of the disk integrated measurements, LHR naturally lends itself to resolved or high spatial resolution measurements, as there's no SNR penalty going to higher spatial resolutions. There's the phased array imaging, which I had mentioned before, and also in parallel, as I presented earlier, we are already looking at some greenhouse gases. Thanks. I'll take questions.
Wonderful. Thanks, Connor. Some great stuff. As per the usual, for folks that have questions, feel free to throw your hand up in Zoom and call on you. Drake, go ahead.
Okay, first of all, can you hear me?
Yeah.
Okay, good. Connor, so one way to improve the signal to noise would be to use a multi-channel RF spectrometer to measure all those intermediate frequencies simultaneously. And I didn't fully understand why you don't do that. It seems to me that at least even years ago, there were acousto-optic spectrometers that have very high bandwidths that maybe could be implemented. But of course, then you have to calibrate one channel versus the other to get a high signal to noise. Can you comment on that?
Sure. Yeah, let's see, I'll go back to this slide. Yeah, essentially what you described would be equivalent to this this first method here. In particular, I put it here as something that's unfolding because just taking, I guess, what would be the two sidebands on either side of the LHR would be folded onto themselves on just a traditional RF spectrum analyzer. And that was something that I wanted to avoid, mostly because where we're looking, the water lines are on both sides. There's just complications that I didn't want to have to deal with.
Yeah, you would have the double sideband problem. Yeah.
Yeah. But if you did split it up and detected it with two different lasers, did straight up digitizing and then just through some numeric processing, you can get both of those sidebands at the same time.
Yeah. Let me sneak in another question here. So you wouldn't, in principle, you wouldn't need the laser comb if you could stabilize your local oscillator some other way, like with a lamb dip or something like that. Is that correct?
Yeah.
Okay.
Yeah, I think there was like an early LHR stuff in the mid-infrared, maybe around 10 microns, that did some pretty interesting actually wind velocity measurements on Venus's atmosphere.
Yeah, that was Jeff Gold's
sort of method where they lock the laser.
Yes. Yep. Yeah, but that of course has its own technical complications.
Yeah. The way we do the dither lock is we actually have one CW laser, we lock it to the comb, and then we measure that, the dither to CW laser against the first one. So a comb is also a good way to lock a CW laser. Makes it pretty easy.
Thank you.
Other questions? I've got one, Connor. So I think you had a little teaser of it on the last slide, but what are the prospects for orthogonal polarization state measurements, simultaneous orthogonal polarization state measurements?
Well, at the very least, that's how we are. We have implemented sort of a 2-channel setup where we have a polarization beam splitter doing that. We have not actually run them in parallel yet, but it's all there. We just need to try it out.
And there's a quick follow-up. Are you limited by the polarization stability in the fibers? I'm trying to think of all the things that could mess with your intensity as you're mixing, polarization fluctuations being one of them, perhaps.
Yeah, no, that's a good question. It's one I'm not quite sure about. Assuming that there's roughly equal, that there's not a strong sort of frequency shift between the 2 polarizations that we're measuring or could measure, it shouldn't be a problem. For instance, like the magnetic field, the left and right polarization should be shifted, but over the entire surface of the sun, I think they'll average down to something more reasonable. Also, at the moment, we're not really doing anything to select the actual axis that the polarization is getting split on. So that is a further complication. It's just going into a single mode fiber. Polarization is getting scrambled as it goes into the lab.
Got it. Thanks. Other questions? Drake, is that a former hand or is this a new one? Oh, you're muted.
Former hand. I'm sorry, I'll take it down.
Readout
right.
complete.
Other questions? Well, I've got another. Well, other people ruminate. So, Connor, you folks have made this into a beautifully compact package. Are there plans to replicate this now that we have a family of these, specifically these trackers, in various places now at different EPRV instruments?
I don't think there's any hard plans, but I know that idea came up at the EPRV conference.
Is the main, I suppose the main bit of complexity is the sort of local oscillator assembly, comb plus local oscillator assembly.
The local oscillators, those are little DFB lasers. They're in like a butterfly mount, so those are pretty easy to pack in. The frequency comb that we're using, that wouldn't really be one that you'd move around, but I think you can get frequency combs, or at least I've built ones that are compact enough to do what we would need for this particular project. It's actually one in the HPF comb. There's an auxiliary one in there.
Well, I for one would be quite excited at that prospect. Perhaps we should talk further down the road.
CCD readout complete.
Any other questions, folks online? All right. If not, well, thank you very much, Connor. Wonderful talk, some great work, and we'll reconvene here. I don't know when. I'm not the usual host of this, but at the next colloquium. So thank you all for joining, and thank you again, Connor.